Good morning. Today we'll be talking about the kinematics portion of Physics 1. Physics 1 is the study of motion, an object's motion in terms of its acceleration, velocity, and spatial position, disregarding the forces that act on the object. Let's talk about position first. Position, represented by the letter S, as it stands for spatial location, is where an object is located. On the topic of position, let's talk about displacement. Displacement is change in position. Its units are in meters and it's a vector. Therefore, you must specify its magnitude and direction. It is also not the same thing as distance, and this example will prove it. So, suppose we had a whole loop and then one entire revolution covers 400 meters. So if we were asked what was the distance covered for one entire loop, it's obviously 400 meters. However, if we were asked the displacement, a lot of students would think it's 400 meters. However, displacement, recall that it's change in position, so how far it is from the initial position. Therefore, if one ends up back here, then the displacement is 0 because they are 0 meters away from their initial position. Okay, now let's talk about something related to initial displacement, which is velocity. Average velocity is change in spatial location divided by change in time. As you can tell from the arrows, velocity is a vector. Average velocity is also the final velocity plus the initial velocity, all divided by 2. Like displacement, velocity is also a vector, as I previously said, and its units are in meters per second. So let's do an example. Suppose a ball travels 5 meters in a time span of 2 seconds. What is its average velocity? Okay, so recall that average velocity is change in spatial position over change in time. So spatial position final minus spatial position initial divided by time final minus time initial. Spatial position initial and time initial are both 0, and we know that spatial position final is 5 meters and time initial is 2 seconds. Therefore, to find the average velocity, we would divide 5 meters by 2 seconds. Doing that, we get an average velocity of 2.5 meters per second. Alright, now that we got velocity covered, let's talk about acceleration. Acceleration is change in velocity over change in time. Note that when we say change in velocity, it's a change in vector. Therefore, it's not just change in magnitude we're talking about, we're also talking about a change in direction. So acceleration, like velocity and position, are vectors, and its units are in meters per second. A little side note here, a constant acceleration does not mean constant velocity. When velocity is constant, meaning it's constant in both magnitude and direction, same magnitude, same direction, the acceleration is 0. Since we got that cleared up, let's do an example. Suppose a ball travels at an initial velocity v0, and then after 3 seconds it bounces off with the same velocity but in the opposite direction. What is its acceleration? So its acceleration, it will be its final velocity, which is negative v initial, subtracted by its initial velocity v initial, all divided by 3. So that will be our expression for acceleration. The negative just means it's going in the opposite direction. Speaking of direction, for my velocity example, I should have specified that it was 2.5 meters per second east. As velocity is a vector, you must specify both its magnitude and direction. Now that we got position, velocity, and acceleration down, let's talk about something that connects all of them together. Uniformly accelerated motion, or UAM for short, plus the big 5 equations. The big 5 UAM equations. So you would use these equations when the acceleration of an object is constant. Now let's talk about all the big 5. The first one, when acceleration is missing or you don't know what acceleration is, you would use this equation. The position of an object equals its average velocity, which is the same as what I said earlier, final velocity plus initial velocity all divided by 2. This is the exact same expression, multiplied by time. The second equation, which you would use when not given the spatial position, the change in spatial position, is final velocity equals initial velocity plus the acceleration times time. The third equation, when you don't know what the final velocity is, change in spatial position equals the initial velocity times time plus half multiplied by acceleration times time squared. The next equation will be very similar to this equation. change in spatial location equals the final velocity times time minus half times at squared. So this is when you're missing initial velocity rather than final velocity. And the last equation where you're missing the time, final velocity squared equals to initial velocity squared plus 2 times acceleration times the change in spatial position. Free fall happens when an object is traveling near the Earth's surface. The acceleration is constant. It's a constant negative 9.8 meters per second squared. And here are some free fall graphs. Let's talk about the vertical components first. The vertical components change in vertical position or vertical displacement as a function of time. You'll get a quadratic that looks like this. And then its vertical velocity as a function of time, you'll get a negative slope that's decreasing. And then the acceleration as a function of time is a constant negative 9.8 meters per second squared. On the horizontal components, you'll notice that it's linearly increasing. The change in horizontal position as a function of time is linearly increasing. And then the vertical velocity as a function of time is constant as there is zero acceleration in the x direction. Let's talk about the slopes of these graphs and the area under the graph. One might think that you'll need calculus, which is true. You would need calculus to figure out what graph it is. However, we'll just talk about what the area and the slopes are. So the slope of this graph, or if you're a calculus student, the derivative of position as a function of time gives you velocity. Hence why you have this decreasing slope. Because what happens is the slope is decreasing as it goes up. It becomes 0 here, the slope of the tangent, and then it starts increasing in the negative direction. Hence, you get this. And then when you differentiate this, it's going down at a constant rate, therefore you get the negative 9.8 meters per second squared. The area under a velocity as a function of time curve gives you displacement, the slope of this curve gives you acceleration, and the area under this curve gives you change in velocity. Not this, change in velocity, not the same thing. Similar with here, the area under this curve will give you acceleration, it will give you change in position, sorry, and the slope, the derivative of this graph gives you 0, its acceleration, which will be 0 as this is constant, and then the slope of this graph will be the velocity. On the topic of freefall, let's talk about something that relates, or it's related to freefall, also known as projectile motion. So, projectile motion exists because when an object travels in freefall, realistically, we know it's not going to travel in a line. It's going to go in a parabolic motion, as you see here. So, what happens is that the object will travel up with an initial velocity, v0, and then eventually, at its peak height, it'll have a final vertical velocity of 0. And then as it comes down, it'll have another initial velocity, which will be faster than this one due to gravity. So let's talk about what happens in the x and y directions. In the x directions, we have this one UAM equation that change in horizontal position or horizontal displacement equals to horizontal velocity multiplied by time. Now, in the x direction, horizontal velocity is constant due to the fact that acceleration in the x direction is 0. And then for the y direction, to solve for whichever, such as vertical displacement or vertical velocity, you would use the second to fifth UAM equations I showed earlier. The acceleration in the y direction is a constant negative 9.8 meters per second squared, or g, and the only thing that connects the x and y directions together is the time. Let's do an example together. Let's say a ball had a horizontal velocity of 15 meters per second, and it travels a vertical displacement of 100 meters in 3 seconds. What is its range, or its horizontal displacement? If you didn't notice already, this question is actually really simple. We already got everything. We don't need to know the vertical displacement, as that is irrelevant, because we're already given time and the horizontal velocity. So recall that the horizontal displacement equals to the horizontal velocity multiplied by the time. In this case, 15 meters per second multiplied by 3 seconds, which will give us a total of 45 meters. Alright, let's do another example. So suppose a projectile was launched with an initial velocity of 40 meters per second at 30 degrees above the horizontal. What is the time? So if we look at the y direction, So if we split our velocity into components, we see there's a horizontal component and a vertical component. In this case, because we don't know what the range is, or the horizontal displacement, therefore we can't find the time, it's better off to use the vertical component. So recall that the vertical component, in this case, we have to use trigonometry to solve it. Recall that sine theta is the opposite side, opposite of the angle, divided by the hypotenuse. In this case, Vy divided by 40. So our vertical velocity, or the vertical component, will be 40 multiplied by sine 30. And sine 30 is 1 over 2. Therefore, Vy, the vertical velocity component, is going to be 20 meters per second. Now, we need 2 more variables to solve for the time. If we have 3 variables, we can solve for the other 2, and you get 1 happy physics student. So, now that we have the vertical velocity, let's see what else we have. We also have the fact that acceleration in the y direction is a negative 9.8 meters per second squared, because acceleration in the y direction is always constant. Now, we have 2 variables, and you might be stuck now thinking, what is our last variable? Because we only have 2. This one's not as obvious to so many students, but notice how when the ball's initial vertical position is the same as its final vertical position, meaning the vertical displacement is 0? Yes, good. Now that we figured that out, let's solve. Based off our big 5 UAM equations, let's see what we have. We're trying to look for the time. We have vertical displacement is 0, we have acceleration, and we have initial velocity. So let's use big equation number 3. The change in spatial location, an object's spatial location, equals to its initial velocity multiplied by time, plus half at squared. So, recall that our vertical position displacement delta y is 0, and that will equal to 20 times t because we don't know what the time is, plus half, and in this case we know what a is, it's just going to be g, so we just put g there, and then t squared. Now, let's do some factoring. We can factor 1t out, therefore we get t multiplied by 20 plus half, or in this case, let's make it even better. Let's make it even easier. So we know g is negative 9.8, therefore we can just say it's minus 4.9t, and not t squared because we factor out a t. Notice how now that we can take out 1t, because the t will cancel out, we can't get t is equal to 0, that's just unrealistic. So now we get 0 equals to 20 minus 4.9t. If you're in AP Physics, you would use that g equals 10, but for precision purposes, we will use g equals negative 9.8 today. Okay, so now we just gotta do a bit of algebra. We add 4.9t to both sides. Thereby, we get 4.9t on the left. Now, 4.9t equals to 20. Divide both sides by 4.9, and you get that t equals to 4.08 seconds. But because of sig figs, we're going to say t equals to 4.1 seconds. We'll leave it off at 2 seconds, as 1 second will be pretty imprecise. Now, our last example. Alright, so our last example, we're given a velocity v over there, and it's launched at angle theta. It travels a whole range r at time t. So what this question wants is that they want us to derive an expression for r, the range, and h max, which is the maximum vertical height the projectile reaches. So let's start with the range first. Recall that we can split the velocity into its horizontal and vertical components. Because this is range, we're going to go vertical components. Recall that cos theta is the x component divided by the hypotenuse. Therefore, Vx, or horizontal velocity, will then equal to the v multiplied by cosine theta. And then for the range equals to the horizontal velocity multiplied by the time. Therefore, our range will be v cos theta times t. And now we want to, how will we go about now? Well, you see, the one thing, as I said earlier, that connects horizontal and vertical together is the time. So let's isolate for time. Divide both sides by v cosine theta, you get a t by itself, and now you get that t equals to r divided by v cosine theta. Now, let's figure out how we would solve for h max. Recall the third UAM equation I mentioned. The change in spatial location equals to initial velocity multiplied by time plus half multiplied by at squared. So let's use that equation to solve. H max, or let's just put it as h to make things simpler, equals to v sine theta, the vertical component, multiplied by our new expression for time, r over v cos theta, plus half, and in this case a is g, so let's just put g in this case, half g multiplied t squared. In this case it's going to be r divided by v cos theta squared. And notice here how the v's cancel out and you get sine theta over cos theta. The trigonometric identity for sine theta divided by cos theta is tangent theta. You will need to know this for physics, higher level physics, and some further trigonometric identities, but we'll talk about those in a future time. So after all this, we get that h equals to r tangent theta plus half g multiplied by r squared over v squared cos squared theta. Okay, good. Now we have an expression for our height. Alright, so now how do we find an expression for range? Well, if we look over here, when the time equals half of its actual travel time, we get that negative v sine theta equals to g times time, and that's our expression for half the time. Therefore, to isolate for time, now we get that time equals to negative v sine theta over g. And the reasons I'm not canceling out the negatives is because g is already negative. So if I took out the negative, you would be saying that time is negative, and that is impossible. So since that's half the time, what would the entire projectile launch time be? Simple. We just multiply by 2 because the vertical displacement is 0. Equals to negative 2 v sine theta over g. So let's recall that our expression for range was v cosine theta t. And now that we have an expression for t, we can just plug that in. So plugging in what we know for t, we get that r equals to v cosine theta multiplied by negative 2 v sine theta over g. Now, another trigonometric identity one must know for the course is that sine theta times cos theta, I'll write it up here. Sine theta times cos theta equals to half sine 2 theta. The actual expression is sine 2 theta equals 2 sine theta cos theta. However, because we have sine theta and cos theta here, that's our actual expression. So, knowing that, we get half sine 2 theta, but then there's a 2 here, so then the 2's will cancel out. Therefore, our answer will be negative v squared, because there are two v's, v times v equals v squared, negative v squared sine 2 theta, all divided by g. So here is our expression for max height, here is our expression for range, and here's one of our expressions for time. This brings me to the end of the lecture. I hope you guys enjoyed it as I enjoyed teaching all of you. In my next lecture, I'll be talking about dynamics. When it's similar to kinematics, the only difference is now you're including the forces that act on the object. Thank you for listening. I will see you all next time.